Recording is rolling. It is Thursday, November 7th. So, class agenda. I do have a few more energy posters I want to go through with you guys. So, I'm going to take the first few minutes of class to do that. And then you guys have a lab page on your desk. It looks like this. Right? Which, ooh, hey, look, that picture right there matches that picture right there. So, the lab's going to be what is the maximum speed of the pendulum pop, which would be at the very bottom, wouldn't it? Because it has maximum kinetic energy there, right? So I have a derivation here that shows you guys the speed. So on your guys' lab, you guys can do the calculation based on the geometry, right? The angle, the length of the string, and then you guys can measure it with, ooh, you guys have some speed gates there. Do you guys think you can dunk the speed gate upside down, goes right through it, right? And I bet these two cells right here are gonna be pretty close to the same. Right, so here, we'll circle back to that one. All right, what else we got here? Right. You guys know, last couple days we've been working on that energy packet, right? So that 3-page packet looks about like this, right? So you might possibly have that finished by now, or if you got a couple more rows, go ahead and see if you guys can get the last few rows, and then I think tomorrow I want to go over the rest of the solutions with you guys if we have time to do that in class, right? So let's have that. Guys, I'm going to post a link to a video, a YouTube video. Do you guys know the channel? A guy named Mark Rober, right? Mark Rober used to work for NASA. Right now, he makes YouTube videos. So he has a video on a Pinewood Derby cars. Right here, actually, do I have that queued up? So I can slide it over right here. I'm going to post a link to this video. So you guys see he's holding a little tiny car. It's about that big. Right? So you get this in a kit. It's like a little block of wood. It's got some wheels, and you can shape it into a car. And then they race these things. They put them on tracks and they race them. Who's just the fastest? He shows you exactly how to make the ideal car using physics, and he walks through exactly the conservation of energy process that we've been talking about last few days. So that's a really excellent example there. I will post that link and encourage you guys to watch that just sometime over the next few days. Right? Right, and then. All right. Next few days. So Monday, of course, is Veterans Day. There's no school on Monday. Then Tuesday is going to be a weird day. There is FCLE testing. So my first 4 classes are relocated. Guys, I did post to Google Classroom an Excel file that shows where you're going to be testing if you are testing. So a lot of you guys are testing. Excel file shows you where that's going to be. And if you're not testing, then I bet some of your classes might be relocated, and that information is also there. Guys, it's all on Google Classroom. All right, so then we got today and tomorrow, and the next real bit day class is going to be on Wednesday, I guess. All right, so you guys good with agenda, what we're doing? All right, let's go back and hit these posters because there's just a few more I need to do with you guys. All right, we'll round back around to this one, today's lab. All right, so hey, Atwoods, they're back. You guys remember these Atwoods? You guys did this lab. You guys had a pulley, a couple masses. Yeah, you guys remember that? Now, back a few weeks ago, what I was having you guys figure out is what's the acceleration based on these masses. So you would change the input masses and say, well, how much does it accelerate? You guys calculated the acceleration from, let's say, I know it goes so far and so much time, starting from rest, I can calculate the acceleration, right? Something like that. Okay. Now, Atwoods are back, but now in a different context. So let's see, what equation could you get out of this? And then later on, I'm going to say, well, what would be an ideal question to ask? I can get a textbook question. So one thing at a time here. Okay, so I'm looking at the M1, M2 Earth system. So each mass is part of the system in the Earth because, well, there's a gravitational field and they're changing height. So I'll have to include the Earth to make it a closed system. So now I can say this. So guys, this is conservation of energy. Sum of energy at some initial point is equal to sum of energy at some different point. Now it could be different forms of energy. You got potential and kinetic going on, but the number of joules is the same. Here's point A is these blocks are like here. And then point B is after these blocks move to like right here. Right, some height change, right? Guys, does this one move down as much as this one moves up? Is that same height change? Yeah, one's down, one's up. Right. So, guys, let's put together the conservation of energy. I'm going to cover this up so you guys don't see the answer yet. All right, but you guys are going to tell me how to put this together. Oh, now in terms of conservation of energy, so we're thinking when this is moving, what's effectively supplying the energy? Where's the energy coming from to move? Yeah, gravity field, right? Now, which one's moving down and therefore started with all the potential energy? Yeah, the big one, right? And guys, what's the formula for potential energy? MGH, that's right, MGH, right? So I put it in green here because that's you can think of that being like all the source of energy. It's all MGH. So the sum of energy initial It's all from the fact that the large block is elevated and can fall. Okay. Okay. Now that energy is going to go to 3 different places, and that's going to be, you guys see sum of energy final. Well, this truly is a summation because there's going to be 3 different final locations for that energy. Guys, what's one place the energy goes? Kinetic. Is it, guys? Isn't it true? After some movement, these blocks are going to have some speed at the end of that interval. Actually, that's 2 kinetic energies, isn't it? Each block has a kinetic energy. Now, because there's one more place you have to consider for energy accounting. Where else does that energy also go? Okay. Exactly. Yeah. It has to lift block 1. So some of the energy went to lifting block 1. So let's put it all together. There it is. That's exactly what you guys just said. Okay. So the large block falling supplies the energy, goes into 3 places. It lifts the small block. And also at the end of that movement, each block has a speed, therefore has a kinetic energy. So I'm just going to make up some numbers. Suppose the large block falling, you run m times 2, maybe it's like 100 joules. And maybe 20 joules go into lifting the small block. And you have 100 here, 20 here, that's 80 joules left over. Maybe it's like I don't know, like a 50-30 split, something like that, like joules to joules. Okay, so 100 joules here equates to 100 joules also over here. Okay, I guess that. Okay, all right. Let's look at another one. Oh, it's a modified Atwood. Look at there, modified Atwood. So you guys also did this lab where it actually looked more like this when you guys did this lab. This guy was on wheels, right? You guys remember that? Or low friction system, all right, something like that, right? So this one's a little different. But if you read the music of this equation, it's the same thought process, right? So sum of energy and inertia. I have this as an open system. So I actually took the wheels off. This one I have like dragging. The reason I have it dragging against friction is actually because my college physics students have a textbook question where they have it dragging with friction. So I have that. So you have to subtract off force times distance, right? And then you're kind of like the car braking to a stop. We did the same thing the other day, right? And then you're going to end up with some energy at the end, right? So the source of energy, just like the last poster, is the fact that this large block here can fall. It has some MGH. That's this green right here, this MGH, right? So subtract off force times distance of this block sliding up here, right? That friction force times sliding distance, right? Which, by the way, this distance sliding is equal to this height change. It's all the same distance movement. Right? And then you'll have some energy left over, which goes to 4 different places. You got to lift the small block. There's your MGH there. And then 1, 2, 3 blocks all have the same speed, so they each have their own 1/2 mv squared. Right? Right, you guys good? Energy accounting. There you go. Right, you ready for the next one? The next one. Oh, guys, the next few posters are all simple machines that give you some kind of mechanical advantage. I got one rigged up right here, but let's see how this is going to work. And I'll have you guys do a lab. Here's your lab paper. Probably next week. I want to fit this in if I can. Next week should be coming up pretty soon. Right. So what's going on here? So on the side with the spring scale, maybe I can pull it. And then you guys think this really heavy weight is going to be lifted? Yeah. Now it turns out that those forces are not equal. Right. Guys, what if this weighs, let me make up something. Let's say this weighs 60 newtons, right? You guys got that? I'm just making up 60 newtons. Right? Do you guys see that this one string, it from the point of view of the 60 newton weight, it kind of looks like 3 strings, doesn't it? It's kind of like it's being supported by 3 strings. So guess what? It's the tension in the string. If this is 60 newtons, what's the tension? Divided by 3 is 20. 20. Guys got 20 here, 20 here, 20 here. That'll pull up 60 newtons, won't it? 20, 20, 20. So guess how much force you have to pull with on the side of the spring scale? 20 newtons. Yeah, which is the tension in the string, 20 newtons, right? Guys, you only need 20 newtons to pull up 60 newtons. Your strength has just been magnified by a factor of what? 3. Right? 60 compared to 20, right? That's called a 3-to-1 mechanical advantage. Right? And you can see that here. Here I have a 5-to-1. You guys see 1, 2, 3, 4, 5 here and 1. So this weighs 10 newtons. It's your big lab weight, 10 newtons. But there's only 2 newtons reading on the spring scale, right? Because 10 divided by 5 is 2. Right, you only need like 2 newtons for it. You can be a little weak, like, and you still like, whoa, I'm lifting a grand piano. I'm strong, because you know physics. And here's the principle. It's conservation of energy. Work input equals work output. You can amplify your strength, your force. You cannot amplify the amount of energy in the system. I should have asked you guys that as a question. Can you amplify the amount of energy in the system? No. Right, the number of joules is the same. Right. So, okay. So what's the catch? The catch is the amount of string that you pull versus the distance this actually moves up. Do you guys see that those are also not equal to each other? So if I pull this like 30 centimeters, are you guys ready for math? Let's do some math. If I pull this 30 centimeters, take a guess how far this moves up. 10, exactly. Because it's just 30 divided 3 ways. It is 10. Okay? And if you multiply force and distance together, if I'm 3 times as strong, but I got to pull 3 times the amount of string, if I put in 100 joules, I only get out 100 joules. Right? So the energy is conserved. Right? Now, there's something called mechanical advantage. Here's 2 different perspectives. Ideal mechanical advantage is just the geometry of the system. I see it 3 to 1. That's just in terms of the distance moved, 3 to 1. Okay? Then there's something called actual mechanical advantage. Well, how much are you actually multiplying your strength? Now, I've been making the claim as 3 to 1, but do you guys think realistically there might be a little bit of frictional loss possibly in the strings? Or maybe they're not exactly vertical. It might be a little bit of a loss process. Maybe it's like 2.8 to 1 or something like that. Okay, so it could be a little bit less. Actual mechanical advantage. All right, you guys get that? Right. So that's going to be, again, the lab. I want to get you guys next week if I can. Right. Right. Oh, now you can also get a mechanical advantage doing this. Because what if you have a couple of wheels locked in place relative to each other? Do you guys see like leverage, like a seesaw leverage? Right. So again, small force can lift a very large force, large weight. Right. But the catch is you have to pull lots and lots of string on the side, and this only moves up a little bit at a time. Right. The force times distance equates. Right. 3 to 1 mechanical advantage there. Right. Ooh, you guys ever have like a big old box that's maybe just a little bit too heavy to lift, but you put it on some wheels and you have an incline and like up it goes, like into the U-Haul van? Yeah. So you get a mechanical advantage with an incline. It ends up being this length divided by this height. Is okay, could be 3 to 1. Okay. Right. Here's a full list of simple machines. Okay, so I showed you guys this one. I just showed you guys this one. And then like that wheel is kind of either one of these, you can kind of take it sort of like those wheels lock in place. Got those simple machines. Might possibly have you guys do this. Right. So if you're on a seesaw, I suppose you got a heavy friend and a light friend. Could you put the heavy friend close to the fulcrum and a light friend out here, and then like lift them like that? Right. Now the heavy friend doesn't move up very much. All right, but you can lift something right here. Right? All right, get a mechanical advantage that way. All right, new stuff. You guys ready for new stuff? Right. No, power. Power, I mentioned real briefly a few days ago. Let's circle back around it. Who remembers what SI unit do you measure power in? Starts with a W. Watts. You guys look on a light bulb, so it's like 40 watts, right? That's like 40 joules per second. That's what that means. 40 watts is 40 joules per second. You have plugged into the grid, it's drawing energy off the grid at that rate. Right. So that's a transfer of energy per time. That's a rate transfer of work. That's what that is, right? Now there's a special case of this. Is what if you're pulling up an elevator? You guys see this elevator going up? Do you think there's a motor at the top of the elevator? Like pulling up that elevator, right? Yeah, right. So there's some tension in this rope. Got that? Right. Right. Let's do some math here. Guys, work is equal to what times what? That's right. Force times distance. Right. So you guys see that little substitution? That's okay, right? So this is equal to this, same thing. Right. Ooh, look at this. Guys, what is distance over time? What is that called? Velocity. Yeah. Velocity, speed. Right. So I can substitute that, right? Okay, that's where I'm getting this one from. All right, so guys, this is another classic physics textbook question is, suppose you're pulling up an elevator at some speed. What's the power output of the motor at the top of the shaft from pulling it up? Right? And this is always the answer. So it's just whatever the tension of the string is, times however fast the elevator is being pulled up. That's all. Right? You do that too. So this and this and this are the same thing. Okay. There's a tricky twist on this is, what if the elevator is accelerating? In which case, this tension force would be different than the weight. So you got to be careful with that. It might be m times g plus or minus a. And the speed would just be instantaneous to one time, right? But all right, that's a little tricky version. All right, you guys good? All right. I just got a couple more posters for you guys. All right, so let's go hit something a little bit more complex here. On your guys' 3-page energy table, the last question is a challenge question. It involves 2 asteroids gravitationally attracting. You guys remember that? And I told you guys, you don't want to use the MGH version of potential energy because this gravity field is always changing. That's also true if you're sending a rocket all the way to the moon. This gravity field is not constant, so you cannot use just plain MGH. Right? You have to use the universal form, which is this green cell right here. which don't do too often in this class, but if you go to special scenarios, right? Right. And I want to show you guys a couple of things with this. One is that this does simplify to MGH for small height changes, right? And when I say small height change, I mean relative to the radius of the planet, so that this gravity field is approximately constant. Let me show you guys that first, right? And then something else later. Right, so here we go. Right, so we're starting off with universal potential energy is negative GMM on R. It's negative. That's interesting. Right? This almost looks like GMM over R squared. Guys, GMM over R squared. That was a what type of property in physics? Was that a mass, an acceleration, a force, an energy? What is GMM over R squared? It's a force. It's a force, right? Okay. And force times distance could be like work or energy, right? Oh, okay. So if you multiply by R, GMM over R squared times R, one of the R's cancels, it does look like this. Okay, so it's negative. Just take my word for that now. I'll come back to the negative later. But for now, let me just show you guys the proof. Okay. So let's say go from like the top of a crazy tall tower down to sea level, or the top of Mount Everest down to sea level. That could be a pretty big height change, right? Okay. Except in terms of the radius of the Earth, actually, it wouldn't be so big. Like if the Earth was like the size of a bowling ball, then the difference between the height of Mount Everest to sea level is like a tiny little scratch on the bowling ball, right? So it's hardly anything compared to the radius of the Earth. Right? Okay, so let's go from the top of a tower down to sea level. Could this be R2 and this could be R1, and the difference between those two could be H, right? Okay. So hold on to that idea. So we're at the top of the tower, we got GMM over R2, I should say negative GMM over R2. And at the bottom of the tower, we've got negative GMM over R1. Let's say I want to say, what's the difference in potential energy? I would subtract those two, right? Right. Ooh, do I need a common denominator? Guess how do you get a common denominator? Multiply R1 over R1. Multiply R2 over R2. Right. Okay, that's this brown step right here. You guys see this brown step? Right. One more thing. Guys, minus a negative. Is that same thing as plus a positive? Okay, so that's this blue step right here. Okay, you see that? All right, so I got that. Right, now I'm gonna combine these together. I'm gonna factor out the GMM. So I got the difference in R's here. Okay, you guys got that? Here. All right, next ooh, guys, what is R2 minus R1? What is that? Yeah, that's just H, right? And what about all this brown in the middle? GM over, okay, I have R1, R2. Because if R1 and R2 are almost the same thing, can I basically treat that as R squared? Right? Guys, what is GM over R squared? Close. Gravity field. Guys, that's the gravity field of the planet, isn't it? That's like lowercase g. Okay, so I have an M there. I have a lowercase g there. I have an H there. Hey, that's MGH. Haha. That's MGH. You see it? All right. That's where that comes from. All right. And then, all right, I'm going to do one more thing with that universal gravity. All right, you guys ready for this? You guys ready to stretch your imaginations a little bit? I need to explain this poster. All right, so escape speed. How fast do you have to get a rocket going so that you can cut off the engines and it's still moving fast enough to go escape the gravity of, say, Earth, if you're sending away from Earth? How fast is that? Okay. All right, so I need to explain the story backwards. So here's the backwards version of the story. Let's say I have a big old empty universe except for two objects. And on the left side of the universe, I have the Earth. And on the right side of the object, I have a little tiny rock. You guys see that? The Earth and the rock. Let's say they're like opposite edges of the universe. Do you think these feel a tiny, tiny, tiny gravity force between them? Right? And they start pulling together. And maybe the Earth barely moves, but this rock is going to basically cross the entire universe, right? Let's say a billion years later, this finally comes from the edge of space and crashes onto the Earth, right? Like, it takes a billion years for it to cross the universe. You guys get that? Right. How fast does this crash into the Earth, falling from the edge of space? Is it infinitely fast? No. Is it the speed of light? No, nowhere close. Well, let's say, how would you figure out how fast? And here's how we're going to do this. We're going to do conservation of energy. So when these are hanging out, just floating at the edge of the universe to start with, do they have any kinetic energy? No, because they're not moving. So 1/2 of v squared, that's all 0, 0, 0, 0, right? Let's just go ahead and let the whole energy, the total energy be 0. You guys got that? Right, this is a little bit abstract. We'll let the total energy be 0. Now, as they fall towards each other, isn't that a decrease in potential energy? Right, like a height. Because it's like they're losing height, right? Like MGH. If you start on the top of a hill, you go to the bottom, you're losing potential energy, right? Yeah, right. And instead of a hill, we just have like the width of the universe. But the same idea, right? Right. But if you started with zero energy and you're losing potential energy, that's why this would have to be negative, right? Okay, so in a universal sense, gravitational potential energy is always negative, right? But here I'm saying conservation of energy. So kinetic energy, which is this 1/2 mv squared, and potential energy, which I'm using the full form, negative gmm on r, that always has to zero out. At the beginning, that was true. As this is falling towards the Earth, is true. And right about as this is about to crash into the Earth, that's still true, right? Right. So, guys, what variable cancels out? Yeah, the mass of the rock goes away. So if you have a small rock and a big rock, I guess they crash at the same speed, basically. Right? And then if you solve for this v, that would be how fast is it crashing into the Earth, falling from the edge of space. And it turns out to be this expression here. Right? Well, guys, if you just took this rock and you turn around and threw it straight up into the sky at that speed, it would have just enough speed to go back to the other edge of the universe. Oh, that's what escape speed is. Okay, so there you go. That's escape speed. Okay, that's where it comes from. All right. So you guys get there? There's the rest of the posters. Now let's go back to the main activity for today. We're back to this right here. Right? And you guys have your lab paper version. So what I have you guys do is do trial A, B, C, D, E, whatever. You guys got some different lab weights. You can change out the masses. If you wanted to, you could change out this length. If you want to, you could change out this angle. It's a little bit loose as to what the independent variable is. Or if you want to, you could mix and match all three. So you could treat any or all of these as independent variables. That's okay. But really what I want you guys to see is just trial by trial is the fact that you can calculate what the speed is at the bottom using conservation of energy and basically giving you the answer right here. But ideally, you should be able to solve this, right? Yeah. If you want to get the most out of this class, see if you can. See if you can maybe turn over the paper and solve it from scratch and on the back, if you like that. Right. And then you have the speed gates where you can turn this upside down. This goes through the speed gate, and you can grab the value empirically. And I bet you guys these two cells are going to be almost the same number, about the same number, right? Whether you calculate it or measure it empirically. So go ahead. You guys got the rest of the class. Get a few rows of data, see that they're the same, and then turn that into the grade tray by the end of class. All right, and that's a wrap on this video.